I'm Bill Ashmanskas. I teach physics and electronics here at UPenn, and when I'm not teaching, I work on electronics design, both for medical imaging and for particle physics experiments. I designed this board about 10 years ago to read out 1/24th of this research PET scanner. In PET, a chemical tracer injected into the patient undergoes radioactive beta decay, emitting a positron, which is the antimatter version of an electron. The tracer most commonly used in positron emission tomography is so-called FDG, which is a version of glucose in which one oxygen atom is replaced by this radioactive isotope of fluorine called F18. When the F18 decays with a half-life of about 2 hours, this isotope of oxygen appears in place of the fluorine and a positron is emitted, in addition to this ghost-like particle called a neutrino. After traveling about a millimeter, this positron annihilates with an electron in tissue. Your body, of course, is matter, whereas a positron is antimatter. The result of this annihilation is two back-to-back photons. The energy of each of these two photons, which is in the X-ray range, is 511 keV, which by Einstein's famous E equals mc squared is the rest energy of an electron, which is the same as the rest energy of a positron. The mass of an electron, 9.11 times 10 to the minus 31 kilograms, is the same as the mass of a positron. And if you say that in more atomic or nuclear physics units, this 9.11 10 to the minus 31 kilograms is the same as 511 kiloelectron volts when you put it into energy units by multiplying by the square of the speed of light. So this 511,000 electron volts, the energy of this X-ray photon produced in positron annihilation, is about 38,000 times the perhaps familiar Rydberg constant, 13.6 electron volts, that you might have seen if you studied chemistry or studied the physics of the hydrogen atom. Since you might remember that hydrogen spectroscopy typically involves photons that are in or near the visible range, it seems plausible that this energy is equivalent to tens of thousands of visible photons. So in fact, if you could convert all of the energy of one of these X-rays into visible photons in the visible wavelengths, you would get something like 200,000 visible photons, just taking a typical wavelength in the middle of the visible spectrum. In a PET scanner, the patient is surrounded by a ring of crystal scintillator, which you can imagine is occupying the space between these two concentric circles. So if a positron is emitted at this location, then it will soon meet a nearby electron. We said that happens within about a millimeter, and they then annihilate, and the result is two back-to-back X-ray photons, each of which has an energy which is equivalent to the rest energy of an electron or positron, 511 keV, and somehow we want the PET scanner to be able to detect the passage of these two back-to-back X-ray photons. Of course, it's not just one pair of photons. What we'll see over time is the passage of many pairs of back-to-back photons. So by reconstructing where all these lines cross, one gets an image of where the positron decays occur in the patient. PET, in fact, gives an image of metabolic activity, at least FDG PET does, rather than giving an image of anatomy as a CT scan or MRI would, because the radio-labeled glucose, the fluorodeoxyglucose, accumulates where glucose metabolism is occurring, so the positron decays occur where glucose metabolism is happening most rapidly. So this turns out to be useful for staging cancer. Somehow we want to convert the passage of these X-ray photons into data on a computer hard drive. The first step is the passage through this scintillator. A scintillator turns an X-ray photon into tens of thousands of visible photons. So in this case, we use in our research scanner an inorganic crystal scintillator called lanthanum bromide, which gives us about 32,000 visible photons for the initial 511 keV X-ray. So that if you do the math, it turns out that it converts something like a quarter of the energy of this X-ray photon into useful visible photons that we can then subsequently hope to turn into information on a computer hard drive. So what is the next step? Behind this scintillator is an ingenious device called a photomultiplier tube, whose job is to turn visible photons into a pulse of electric current. So for this scintillator, an X-ray photon went in and tens of thousands of visible photons came out. For this photomultiplier tube, its input is visible light, small numbers of visible photons, and its output is an electric signal, so a small electric current. So we will get a number of electrons out in proportion to the number of photons that go in. And the multiplication factor is typically hundreds of thousands or maybe even millions. And that's useful because it gives us an electric current which is big enough to measure with electronics, even for just a few tens of thousands of photons. So for our system, a typical number might be that for one 511 keV photon going into the crystal scintillator and a few tens of thousands of visible photons coming out, then what comes out of the photomultiplier tube would be, let's say, a few hundred picocoulombs. Right, so that's something like 300 times 10 to the minus 12 coulombs, or 0.3 times 10 to the minus 9 coulombs, delivered over an interval of several tens of nanoseconds. And since this is physics, we might as well evaluate how many electrons this is. So if we divide by 1.602 times 10 to the minus 19 coulombs per electron, we get something like 2 billion electrons in this little burst of current that comes out over the course of several tens of nanoseconds into our readout electronics. So if we were to make a graph of this electric current as a function of time, so we'll use capital I for current and T for time, you would see that shortly after the passage of the X-ray through the scintillating crystal and the subsequent passage of visible photons into the photomultiplier tube, we would see a pulse of current which rises very quickly in a fraction of a nanosecond and which then falls off with the shape of a falling exponential with a time constant of maybe 25 nanoseconds. And so this width, the time it takes for most of the current to arrive, is a few tens of nanoseconds, maybe 50, 60 nanoseconds. And then the area under this curve, which would be total charge, is a few hundred picocoulombs, which is the equivalent of a couple of billion electrons. We then want to detect this pulse of current with a system of electronics and record it into a computer. While we're here looking at this cartoon of our PET scanner, let me just give you a few numbers for perspective. So the crystal scintillator is in fact about 3 centimeters thick, and the scintillator is not a monolithic block. It's divided up into rectangular crystals. So the cross section of each crystal is 4 millimeters by 4 millimeters, and it's about 30 millimeters thick. And being separated into a grid like this means that if you can identify which crystal was hit, then you can figure out where along this circumference the X-ray photon passed. So around the circumference of this scanner, there are about 40,000 of these 4 millimeter by 4 millimeter by 30 millimeter crystals. And those 40,000 crystals are imaged by, in fact, only about 400 photomultiplier tubes. And the photomultiplier tubes are arranged in a pattern like this, so that by the pattern of light sharing, you can figure out which crystal was hit. And when you figure out which scintillating crystal was hit, you can figure out where the X-ray photon went. It doesn't actually pass all the way through. It gets partway through and then undergoes a photoelectric interaction. So then around the circumference we have 432 of these photomultiplier tubes, and that means we need a system of electronics to read out 432 electrical currents. Of course, this is supposed to be a talk about electronics. So that brings us back to the circuit board I pointed at the beginning of this talk. And one of these circuit boards, of which there are 24 to read out a complete scanner, will read out 1/24, a 15-degree slice of this PET scanner. Since there are 432 total photomultiplier tubes, that's 18 photomultiplier tubes read out by this board. In addition, we have 6 overlaps from the adjacent 1/24 of the scanner so that we don't miss things on the edges. The electrical signals, the little currents, all come in on the back side of the board. On the front of the board, you can see a repeating pattern that occurs 10 times. Each one of those patterns reads out electrical signals from one of these regions centered on A, B, C, D, E, F, G, H, I, J. I told you before we do light sharing to identify which of these 4 by 4 millimeter crystals is hit, since each crystal is much smaller than 1 PMT. So for instance, if we see a crystal hit somewhere around here, to identify that, we would read out this block of 7 photomultiplier tubes centered around point B on the diagram. Or for instance, we might see something down here, and then to get complete information, we would actually want, in addition to this 18 set of PMTs, we would want some information from this overlap region. And for that reason, we have these connectors at the 2 edges of the board. These receive signals from the adjacent board on one side, and these transmit a copy of signals to the adjacent board on the other side. This connector over here is for exchanging data with a so-called coincidence unit that tells us whether something over here and something on the opposite side over here happened at the same time. A key enabling technology of this board is the chip that you see here, 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 and here. It is the so-called DRS4 chip made by a particle physics lab in Switzerland, and it is a so-called oscilloscope on a chip. In just about any laboratory, you will see an oscilloscope. In fact, we'll use one in a moment ourselves, which gives you an image of a voltage versus time. I told you before that what comes out of the photomultiplier tube is a small current, but if you run that current through a resistor, then via Ohm's law, you can get a voltage which is proportional to that current, and it's a little more complicated than that because we use a system of amplifiers, but essentially we get a voltage versus time which is proportional to the current versus time that comes out of the photomultiplier tube, and this amazing chip gives us an oscilloscope-like picture of that signal which we can then process. Right next to each DRS4 chip is an analog to digital converter known as an ADC, which turns the picture recorded by the DRS4 chip into a sequence of bits that could be eventually transmitted to a computer, and then coordinating all of the activity of the board, reading the large numbers of digital signals out of all of these analog to digital converters, is a field programmable gate array, which is a device that allows you to implement very fast and very complicated digital logic, which to some degree means a gigantic number of Boolean truth table operations. Finally, on this quick tour, over here in the top right corner is this little board called MicroZ, which takes all of the signals collected by the big FPGA, reformats them, and sends them out over an Ethernet network cable for processing by a real computer. If you had told the teenage version of Bill that someday I would know how to design and build electronics to read out a PET scanner, I would have thought that sounded like a dream come true. It is, in fact, really cool to know how to build electronics to do something as sophisticated as reading the data out of a PET scanner. What set me down this road about 20 years ago when I was a college student was taking a 1-semester introduction to electronics taught in the physics department. That gave me enough of an introduction to electronics that I could learn a whole lot more on my own and through a sequence of jobs that I held after graduate school. The only prerequisite for that introductory electronics course was knowing the basics of electric circuits that you learned in the preceding module, such as Kirchhoff's voltage law, Kirchhoff's current law, Ohm's law, as well as the basics of some other circuit components like capacitors and inductors. I don't want to claim that you're going to leave this course and know how to go out immediately and do something really big, but learning the basics of analyzing circuits is a key prerequisite for taking a real electronics course, and then taking an electronics course is actually an incredibly empowering way to learn a whole new domain of tinkering. Alas, every journey of 1,000 kilometers begins with a single step. So let's move on to talking about something that actually is accessible at this stage of your learning. So I'm going to give you a quick tour of a couple of boards made by a hobbyist company called Adafruit, which you can program in an environment called CircuitPython, which is supported by Adafruit. This little board in the picture-in-picture, which we'll just look at for a moment, has a whole bunch of neat peripherals built into it. So when you plug it in this case, I programmed it to read out and display a whole bunch of its built-in peripherals, including, well, there's an accelerometer, a gyroscope, a magnetometer, a pressure sensor, okay, so you can get the ambient air pressure, a temperature reading. I guess it's your choice whether you display the result in Fahrenheit or Celsius. So it's telling me that the temperature is 74 Fahrenheit, though somewhat annoyingly, this is a temperature on the circuit board, not the temperature in the air in my laboratory here. Humidity, 63%. Then you can see when I'm talking, this microphone level goes up and it goes down when I stop talking, and there's also an ambient light sensor, and if I shine a flashlight on the board you will see the ambient light level go up. I think you can see the accelerometer at work if I wiggle the board, and then you can also see that one of the three components reads minus 9.8, which sounds suspiciously close to G, and in fact if I reorient the board then a different component will read a value suspiciously close to G, and if I reorient the board yet again then yet another component will read a value suspiciously close to G, and I think if I shake, well, I can't shake it and have you see the screen at the same time. Then there's a gyroscope, which I think will notice if I rotate the board. That's pretty neat. And then the magnetometer should be able to detect which way is magnetic north, though I haven't tinkered with that feature yet. So that's a pretty amazing set of features on a tiny little board, and I think this tiny little board, oh, that annoying flashing light, it has some very bright LEDs which I think are intended to illuminate things nearby as if it were your smartphone camera flash. There's also a tiny little LED screen, a couple of buttons, and then on the back, I think if you look at the instruction manual for this device, you can get a tour of all of the little components built into it. And I think some of them are even labeled. So you can see labels that say things like gyroscope plus accelerometer, temperature plus pressure, humidity, magnetic field, and so on. And of course, there's a neat little display with which it can talk to the world. So you can go to the Adafruit website and you can see a little video demonstration of this board, which is more impressive than my little overview. This board does too much for you all by itself. It kind of leaves the fun out. So I'm going to show you how to do some much more basic things in a way that involves wiring things up yourself. So that was the Adafruit CLUE, and here's the Adafruit Metro M4 Express, which I tried out for the first time in our electronics course this past semester. In past years we used Arduino boards, and we wanted this year to try something that could be programmed in Python. It turns out that when you first plug a CircuitPython board into your computer, the board appears as a little USB flash drive, and then on that little flash drive you should see a file called code.py, and if you open code.py you'll see some Python code which you can edit and modify and save with whatever text editor you're comfortable with already on your computer, and as soon as you save it the CircuitPython board will reboot and will run your updated code.py. So you actually do not need to install any software to start developing with CircuitPython. But if you go to the Welcome to CircuitPython page on Adafruit's site, then it will tell you a little bit about CircuitPython, and it will instruct you to install an editor called Mu. So I've installed Mu on my computer, and I'm going to load code.py from the CircuitPy flash drive. And this is the example Hello World program that is provided automatically by Adafruit on the CircuitPython Metro M4 board. This program already uses digital output 2 and digital output 3 right here. Here's 2, here's 3 on the board. So what I want to do is to wire up a couple of LEDs with my external breadboard to see if we can cause this built-in Hello World code to make our LEDs blink. I have here a little breadboard, and if you turn it over and look at the back, you can see there's metal going across here, metal going across here on the bottom, and then there are little perpendicular metal strips going this way. And what that implies is if I plug something in here, then it is connected to anything else in this big top row. If I plug something in here, it's connected to anything else on this big bottom row. That's usually useful for things that want to connect many places, which turn out to be often two places in our circuit called power and ground. So in our case, this might sometimes be 3.3 volts, and this will usually be the ground pin, which serves as the reference voltage for pins going into or out of this M4 board. And then if I plug something in here, it will connect to everything else in that same little column. So this is a way for me to push wires in and have them connect to each other. So I'm going to take my spool of green wire and my wire cutters, and I'm also going to take a spool of black wire, and I'm going to cut two green wires and a black wire that are 10 or 20 centimeters long, just to go back and forth between the breadboard and appropriate places on this Metro M4 board. Then I'm going to strip a few 2 or 3 millimeters of insulation off the end of each wire on each side. So the wires are made of metal, an electrical conductor, and to prevent the wires from making inadvertent connections to things that they should not connect to, the wire is covered with plastic insulation, which is an insulator. It does not conduct electricity. So we want to be able to connect things to the ends of the wires, so we strip some of the insulation off the ends, exposing the conductor. Now I'm going to connect one of my green wires from pin 2. So we have 0, 1, 2, 3, and so on. So I'm going to go from pin 2 on the M4 board to this arbitrarily chosen column, and I'm going to go from pin 3 on the M4 board to this arbitrarily chosen column, and I'm going to go from the bottom row, which I said was useful for things that might plug into many different destinations, and I'm going to find the ground. Going from right to left here, we read V in, ground, 5 volts, 3.3 volts, and then a couple of other things like reset. So I think V in is probably this external connector where you can plug an external power supply or battery if you like. These two are ground. Ground is the reference point on our circuit that we refer to as 0 volts. So really only voltage differences matter rather than absolute voltages. So you can measure voltages with respect to some reference point on a circuit. And conventionally in electronics we call that reference point ground. We say ground is at 0 volts, and then we measure other voltages with respect to that ground point. Because you know from your study of electricity that voltage is always measured between 2 points on a circuit. So when we speak informally, when we're doing electronics, we say the voltage at a point. That means the voltage between that point and ground. So there's always some reference point called ground, which is one of the 2 points between which we measure voltages. So then this is 5 volts. The 5 volts comes from the USB connector in this case. So it turns out most USB devices run on 5 volts. So this little board gets 5 volts from the USB connector. And then on this board, it uses a clever device called a voltage regulator to produce 3.3 volts, which is the voltage that powers this chip, which is the brains of the board and everything else on the board. So when I say this voltage is 3.3 volts, I mean that if you were to measure between here and ground, you would see a voltage difference, a potential difference of 3.3 volts. So I'm going to plug my black wire into one of these two ground connections, and this wire is chosen to be just the right size. I think it's American wire gauge 22, so that it makes a good solid connection either to one of these little headers on the board or on into a breadboard. I have here a handy device called a digital multimeter that can measure voltage, aka electric potential. It can measure current. It can measure continuity to see whether things are connected to each other. It can measure electrical resistance in ohms. So I will put this on DC volts mode. So I will show you that when I put the black wire of the digital multimeter to, well, I can put it down here on my breadboard's ground, but it's the same thing as putting it to ground over here since I have a wire between them. And then I will put the red end of the digital multimeter to, well, I'll try 5 volts first. I think that's going to be, okay, it says 4.911 volts. I think that's what the USB power from the computer is giving us. And then I will plug it into 3.3 volts, and that says 3.299. So that is the 3.3 volts being made on the M4 board with its own little voltage regulator. Now, in my handy box of parts, I'm going to find a red LED and a green LED. An LED is an example of a diode. A diode is a device through which current can flow only in one direction, and there's usually a little triangle and a straight line on a schematic symbol for a diode. So the little triangle gives you the hint that current will flow down but not up. So you can make current flow through this thing in what is drawn here as the downward direction but not the upward direction. These are light-emitting diodes, so you draw a little photon coming out of the diode symbol, and that reminds you that it is light-emitting. And I've drawn the red one in magenta and I've drawn the green one in green, and I'm going to connect the end that is intended to be more negative, so current flows from positive to negative. So this end will be the negative end of the diode, this will be the positive end of the diode. These have names like anode and cathode, but I can never remember which one is which, so I'll just say positive and negative. So I'm going to start by wiring the negative end of each diode to the ground point on my little breadboard. It turns out that when you pick up a diode or an LED, the lead that is intended to be more positive to let current flow is longer than the lead that is supposed to be more negative. This is the shorter lead, this is the longer lead. So this one should be positive, this one should be negative. Here, this is the longer lead, this is the shorter lead, so this should be positive, this should be negative. So I am going to connect a red LED to ground from someplace down here. So it's a little hard to see on the camera, but I plugged it into this column. Then I'm going to plug my green LED with its bottom end to ground and its top end again to this little column over here. And you could say, why didn't I connect these LEDs positive sides directly to pin 2 and pin 3? Well, to make an LED light up, you want sort of tens of milliamps of current to flow through. In general, if you put a DC voltage directly across the 2 leads of the diode, a large current will flow and you can burn out the diode or LED. Let's figure out what would be a sensible resistor value to connect here, and just out of laziness let's use the same resistor value here, so that if this voltage were 3.3 volts or if this voltage were 3.3 volts, in other words, if I measure 3.3 volts between this point and ground, or if I measure 3.3 volts between this point and ground, what current I1 will flow here and what current I2 will flow here if we make each of these 2 points be 3.3 volts. One way that looks like something you might have seen in the past, I'll draw it that way for the moment to keep things looking familiar, is I could put a 3.3 volt battery over here. And then you see that this circuit has 2 branches, so that there is branch 1 which will have current I1 and branch 2 will have current I2. And you can see that this point is directly wired to 3.3 volts, as is this point. And this point and this point are directly wired to ground, also known in this case as the negative end of the battery. So we could use Kirchhoff's voltage rule in each of these cases and say 3.3 volts minus I1 R1 minus whatever the voltage drop is across the red LED equals 0, and 3.3 volts minus I2 R2 minus whatever the voltage drop is across the green LED is 0. Now, it turns out that when an LED is illuminated, the voltage across it is approximately equal to, I'll wave my hand, it's approximately given by the expression, the unit charge, like the absolute value of the charge on an electron, times the the voltage across the LED is approximately Planck's constant times the frequency of the light emitted by the LED. It's actually more convenient to use wavelength. So instead of writing nu, we will write the speed of light c divided by lambda, the wavelength, which then tells us the voltage across the LED is approximately Planck's constant times the speed of light times the fundamental charge, the charge on a positron, times the wavelength that's downstairs. And lambda red is approximately 630 nanometers, and lambda green is approximately 540 nanometers. Let's plug in the number for green. 6.63 times 10 to the minus 34 joule seconds is Planck's constant. 3 times 10 to the 8th meters per second is the speed of light. 1.602 times 10 to the minus 19 coulombs is the fundamental electric charge, and 540 times 10 to the minus 9 meters is a reasonable value for a wavelength of green, and that gives us about 2.3 volts. And then if we were to plug in 630 instead of 540 here for the red LED, we would get right around 2.0 volts, or maybe a little bit less than 2.0 volts. So let's design this for the green LED. So this value will be about 2.3 volts. Then we can say 3.3 volts minus 2.3 volts minus I2 R2 equals 0. So this difference is just 1 volt. So 1.0 volt equals I2 R2. If we want I2 to be several tens of milliamps, let's say I2 should be something like 20 milliamps to keep the numbers convenient. So that is 0.020 amps. Then we can make R2 equal 50 ohms. So then if you take 1 volt divided by 50 ohms, you get 0.02 amps, or 20 milliamps. We're going to use the same resistor for both because it turns out that your typical box of resistors doesn't have an infinite number of different values. So if we also use R1 is 50 ohms, then we'll get I2 this is like about 2.0 volts. 3.3 minus 2.0 is 1.3, so this will be 1.3 volts divided by 50 ohms, which is about 26 milliamps. Dividing by 5 is like multiplying by 0.2, so 1.3 times 20 is 26 milliamps. So this should be something like 26 milliamps, and this should be something like 20 milliamps. Now let's check that the two resistors I pulled out of my box are in fact about 50 ohms each. I can put my digital multimeter into ohms mode, which is where you see the omega symbol, and then I can pick up the resistor with the red and black leads of the digital multimeter, and this reads about 52 ohms, close enough for us. And I'll check the other one as well, just to be sure. Okay, now I will wire things so that the positive side of the green LED is connected to pin D3 on the M4 board, and the positive end of the red LED is connected to pin D2 on the M4 board. Okay, the positive end of the red LED is connected through this 50 ohm resistor to pin D2 on the M4 board. The positive end of the green LED is connected through this 50 ohm resistor to pin D3 on the M4 board. So in fact, this point in our circuit is now connected to pin D2, and this point in our circuit is now connected to pin D3. What I haven't told you yet about the digital output pins of the M4 board is that there are two states, high and low, that an output pin can take, and if a pin is in the low state, then its output is connected to ground. If the pin is in the high state, then its output is connected to 3.3 volts, or whatever the power supply voltage is that's relevant to this digital circuit. But in this M4 board, the voltage corresponding to a logic high is plus 3.3 volts. So a logic high is plus 3.3 volts. A a logic low is 0 volts. So it's as if the battery voltage in our previous circuit is 3.3 volts when the output is logic high, and the battery voltage is 0 volts when the logic output is low. And each output pin of the M4 board gets its own little battery. Just to remind you what we put together on the breadboard, pin D2 comes down to this little column, which then goes through a resistor to this little column, which then goes through the red LED to ground. Pin D3 comes from this little wire to this column, which then goes through this resistor to this column, which then goes through the green LED to ground. So we have D2 through this resistor, through the red LED to ground, D3 through this resistor, through the green LED to ground. This is supposed to look the way it looks on the breadboard, more or less. This is our circuit diagram, and this, of course, is the circuit as we built it. Now, I don't really like the code that they gave us, but I left it there just because it's the Hello World example code that comes with the board. Let's keep the beginning of the code. So we have some imports. Import time, that allows us to count seconds or fractions of seconds. Import board, which I think is where all of the knowledge about pins on the board is defined by CircuitPython. Import digital I/O is how we tell CircuitPython to tell the board to use the digital inputs or outputs of the board. And we're going to say a variable called D2 is digital I/O, that's a module, dot digital in out. I guess that's a class we're instantiating, and we're saying we want to use pin D2 on the board as a digital in out, and we want that direction to be output rather than input. That means that the M4 board is providing an output from its perspective. The M4 board provides what it considers an output voltage, and then we can use that output voltage, which is either 3.3 volts or 0 volts, depending on whether the logic I/O pin is in the high or low state. We can then use it to run a current through our own circuit. And then same thing for pin D3. So that part of their code is okay. So I don't think I care about their counter. I think I'm going to say D2.value equals true, D3.value equals false. This means logic low. This means logic high. And then I'm going to say time.sleep 1.0. This will be very slow, 1 second. And then I can erase all of this junk down here. And then let's just do the opposite. And then we will time.sleep 1.0 again. So let's save that. And I think when we save it, it automatically loads onto the board. And now you can see that these two LEDs are blinking back and forth with a 1 second delay between each change of state. So red is on, green is off, and then there's a 1 second delay, and then green is on, red is off, and there's a 1 second delay, and so on. We could do the same thing with sleep times of half a second instead of 1 second, and save. Okay, that seems a little faster. Maybe we could say 0.2 seconds. That's even a little faster yet. Okay, I think you get the picture. Now let's do something a little bit different. Let's say that we have a button that we can push, and if we release the button, then the circuit will do what it's doing now. But if we hold the button down, then for as long as we're holding the button down, the LEDs will blink slowly. So if we hold down the button, the LEDs blink slowly. If we release the button, the LEDs blink more quickly. That's kind of a silly thing to do, but it'll be an example of using an input pin and an example of using a push-button switch. Our little push-button switch will be an example of a switch. The schematic symbol for a switch looks like this. So the idea is if the switch is open, as it's drawn right now, then no current flows between these 2 points. And if the switch is closed, then there's a 0 resistance between these 2 points. Now somehow we want to use this switch so that when we push the button, the voltage seen by some input pin, let's say we have input pin D4, which we're going to use, these are outputs, and this will be an input. So the M4 board will be able to sense whether this D4 pin is in the high or the low state. In other words, we will put it into the high or the low state, and the M4 board will notice what state we put it in. So we can connect this end to the M4 board's input pin. I guess a reasonable thing to do would then be to connect this end to plus 3.3 volts. And remember, when I just draw plus 3.3 volts there, you can imagine that what I mean is that there's a battery. Here's the 3.3 volt battery, and here I've wired things up to this reference point on the circuit called ground, and here I've wired it up to the positive end of the battery. But usually in electronics we are a little bit informal about our circuit diagrams, and sometimes it's convenient just to draw a voltage and say, well, this is the point on the circuit that supplies plus 3.3 volts without drawing things that look like nice complete circuits you would draw in a physics course. You'll have to excuse me for following that habit. Now, if we do this, then if you push the button closing the switch, then indeed we have a high voltage, 3.3 volts at input pin D4. But if we let go of the button, we have an unknown voltage at input D4. So closing the switch gives us what we want, 3.3 volts, the high voltage. But opening the switch gives us some unknown value. Well, what if I just connect to ground here? That's okay if the switch is open. We have a connection to ground, so we get 0 volts. But now if I close the switch, we have a very low resistance, approximately 0 ohms. I mean, let's say it's a small fraction of an ohm. We have a small fraction, if the switch is closed, we have a small fraction of an ohm between 3.3 volts and ground, and that will cause our M4 board to try to draw too much current from the USB power supply, and the M4 board will then, well, something might burn up, or the voltage regulator on the M4 board may stop working. That's not what we want, because this would be a voltage difference of 3.3 volts divided by a small resistance, like a fraction of an ohm, and so for some short time several amps would flow, and then things would stop working. So that's no good. Instead, what we do is we put another resistor here. So this is a clever trick. So then when the switch is open, we have a connection to ground. It's through this resistor R, but as long as R is some reasonable value, it's a good solid connection to ground. And then when we close the switch by pushing the button, we will have a 0 ohm connection to 3.3 volts, and then we'll have a resistance R to ground. And because 0 ohms is much less than R, so let's say that R will be something like 1 kilo ohm, okay, 1,000 ohms. So then, if this is a small fraction of an ohm and this is 1 kilo ohm, then the voltage that we see here will be very close to plus 3.3 volts. So we will get a logic high voltage here. There is another way we could do it if we wanted to. We could make it so that if the button is not pushed, input pin D4 sees plus 3.3 volts through this resistor, and if the button is pushed, then we have a basically 0 ohm or a small fraction of an ohm connection through the switch to ground, and we have like a 1000 ohm connection to plus 3.3 volts. So the one with the much smaller resistance wins. So that would give us a similar result, except that pushing the button would be low and releasing the button would be high. Here we have pushing the button is high and releasing the button is low. So this was our original plan, so we will stick with it. In this context, R is called a pull-up resistor, and in this context, R is called a pull-down resistor. So the key idea is that 1 kilo ohm is a much smaller resistance than infinity. An open switch is infinity, but it's a much bigger resistance than 0. A closed switch is 0. Now it's not really infinity or 0, but when this switch is closed, its resistance is much smaller than 1 kilo ohm, and when this switch is open, its resistance is much bigger than 1 kilo ohm. So that's the trick with the pull-up or pull-down resistor. So I have in my box of parts a push-button switch. It has 2 leads. I claim that when I push the button, the resistance between the 2 leads is approximately 0, and when I release the button, the resistance between the 2 leads is approximately infinity. I'll show you that with the digital multimeter in just a minute. And then here is my 1 kilo ohm resistor. Let's take Mr. Multimeter and put him in ohms mode, and I can measure the resistance between the 2 leads of the resistor. I hope the answer is close to 1,000 ohms. And Mr. Multimeter says 0.999 kilo ohms. Then I can put the red and black leads of the digital multimeter on the 2 leads of my push button switch. And I'm not pushing the button, and you can see it says 0.L, which is how multimeters in their own obscure way say overload, which means a big value. This is basically saying infinity. Well, as close to infinity as this thing's able to measure. Now if I push the button, then it says 0.3 of an ohm, 0.3 ohms. I let go, it says overload. I push the button, it says 3/10 of an ohm. Okay, a fraction of an ohm. So that's pretty good. That's what we want. Now, how do we wire this on the breadboard? I'm going to cut a piece of red wire because red is the conventional color for power in low voltage circuits. And I'm going to strip some insulation off the two ends of this wire. And I'm going to run one end of this red wire to 3.3 volts on the M4 board. And then I'm going to run the other end of that red wire to this top row, which I said was often useful for distributing things like power. So this will be my 3.3 volt voltage source. Now what I have in effect is a 3.3 volt battery between this top row and this bottom row. The bottom row is my reference voltage ground. The top row is now connected to the 3.3 volt output of this M4 board. So this is really as if I have a convenient little battery here between the top row and the bottom row. Here is my push button switch. The two pins have to be in different columns so that they do not touch each other. See, if I put the two pins in the same column on the breadboard, then the breadboard would always connect the two pins of the switch to each other. I don't want that. So I'm going to put them in two different columns from one another. Then I'm going to cut a tiny little red wire, and I will run my tiny little red wire from somewhere else on my plus 3.3 volt top row to the same column as the left pin of the push button switch. I'm trying to make it look like my schematic diagram. So I have 3.3 volts on the left. On the right side of my switch, I have a 1K resistor, a 1 kilo ohm resistor to ground. So here is my 1K resistor. And I will go from, oh, I see, I should have moved this. I'm going to move this up so I can reach below it. So I'm going to take my 1K resistor and go from the same column as the right side of the switch down to my little ground row on the bottom. Then, if I take my digital multimeter in volts mode, I should be able to look at the right side of the switch and see that when I am not pushing the button, the right side of the switch is at ground, and when I am pushing the button, the right side of the switch is at 3.3 volts. So let's try that. Here is my digital multimeter. Here it is in DC volts mode. It's like a straight line for DC volts. There's a wiggly line for AC volts. The black wire is plugged into this thing labeled common. It has a little ground symbol. The red wire is plugged into this little thing called input, which is the input that you use for measuring voltages or for measuring resistances. It will turn out, if you ever use a digital voltmeter to measure currents, that the current inputs on a digital voltmeter are separate from the voltage input. So here's the input for voltage or resistance. These are different inputs for current. We won't use those today. So I will connect the black lead from the digital multimeter to ground, and then that's over here. Here's the black lead from the digital multimeter connected to ground, and then I will take the red lead and connect it to the right side of the switch, and it says 0 volts. And if I push the button, I'm expecting to see 3.3 volts, but oh no, I see 360 millivolts. I see 0.361 volts. I stopped. It took me a minute to figure this one out. I think I know what's going on here. Now remember, I haven't been using these M4 boards for very long. I think what is happening here, oh, also another hint, an interesting hint is that the light stopped blinking. So it seems like the M4 board really didn't like this. So let me give you my hypothesis for what's going on. I think that this thing that calls itself 3.3 volts on the M4 board is protecting itself from overload by putting a 10 kilo ohm internal resistor. I'm going to say on-board instead of internal. 10 kilo ohm on-board resistor. So I think when I plug into the 3.3 volt, I'm not really plugging directly into 3.3 volts. I'm plugging into this end of a 10K resistor, 10 kilo ohm resistor, the other end of which is actually wired to 3.3 volts. And what makes me think that is if I draw a circuit diagram that looks like that, then what I measure here would be 1/11 of 3.3 volts. And that's pretty close to what I see. Okay, to get the numbers to work out, even though this seems less plausible, I'm going to say it's actually more like 8 kilo ohms. because then if I look here, I would see 1/9 of 3.3 volts, and that makes more sense for 0.36 volts. I haven't looked at the circuit diagram for the board to confirm that, but this seems like a good theory. Another possible theory is that it just has a maximum amount of current it wants to supply to that plus 3.3 volt pin. Anyway, what that means is I have to use a resistor here which is much bigger than 8 kilo ohms to get the result I want. So I'm going to use 100 kilo ohms here. Okay, this is an interesting real-life digression. So I will replace this 1K resistor with a 100K resistor. So you're watching debugging live in action. So here's my 100K resistor, and now I'm still probing that place. So I still see 0 volts if I don't push the button. Now if I do push the button, I see 3.05 volts, which I think should make sense because that should be 3.3 volts times 100 divided by 108. So that seems plausible. 3.3 volts times 100 divided by 108, which is what you'll get if you work out what you expect the voltage to be here when the switch is closed. That should be about 3.06 volts, and I see 3.05 volts. So that's good enough for me. And it turns out this input pin will register its input as high as long as it's pretty close to 3.3 volts. Like as long as it's well above halfway. So now, instead of looking at this point with the voltmeter, let's send this point over to pin 4 and let's configure pin 4 as a digital input. Okay, so I have another piece of green wire, 15-20 centimeters long. I'm going to go from this point on the right hand side of the push button switch. I'm going to go over to digital pin 4 on the M4 Express board. It's a little bit hard for you to see the pins, but here is a 0, 1. Pin 2 was going to our, the resistor above the red LED. Pin 3 was going to the resistor above the green LED. Pin 4 now is going over to this point. So pin 2 goes to this point, pin 3 goes to this point, pin 4 goes to this point, which is on the right side of the switch. The way this looks on the breadboard is the top row of the breadboard is now 3.3 volts, except that there's this annoying resistance in between, which seems to be internal to the M4 board. And we made this little column also connect to 3.3 volts. This little column's on the left side of the switch. This little column's on the right side of the switch. And then from the right side of the switch, we have this 100 kilo ohm resistor to ground. And if you do not push the button, then there's an open circuit here. Oh, this now goes to input pin D4. So if we do not push the switch, then input D4 sees ground through a 100k ohm connection. If we do push the button, then the D4 input sees 3.3 volts. It actually sees a little less than 3.3 volts because there's something like an 8 kilo ohm resistance up here, which is a lot smaller than this 100k resistance, but it's not the 0 that I originally promised you because of a quirk on this M4 board that I was not aware of. Now let's work on the code. So we're going to say D4 equals digital IO dot digital in out board dot D4. D4 dot direction equals digital IO dot direction dot input, and then we're going to say, if it looks as if I'm making this up as I go, I really am. Now we're going to say if D4 dot value, I could say if it equals true, but actually I could just say if D4 dot value, and if it's high that means true. So if D4 dot value, that means the button is pushed. We're going to say time.sleep 1.0 else time.sleep 0.2. And we'll do the same thing over here. If D4.value button is pushed, time.sleep 1.0 else button is not pushed. Okay, let's try it. I haven't tried this before. Let's try it. Okay, so we just added these two lines saying we're going to define D4 as an input pin, and then we say we're going to check the value of D4.value. So if it's high, which comes out as true in CircuitPython, we'll sleep for a long time. If it's not, we'll sleep for a short time. So the LED should blink quickly when the button is not pushed and slowly when the button is pushed. So here we'll do save. Doesn't look as if anything has changed, but let's see what happens if we push the button. Oh, that is amazing. How often does one do something and have it work on the first try? So we push the button, the LEDs blink slowly. We release the button, the LEDs go back to blinking quickly. Slowly. Quickly. Okay, that's pretty cool. Let's try one more thing. I have here a speaker, and let's see if we can get the board to play a tone through this speaker. So on the back of the speaker are two wires. I'm going to connect the speaker to an output pin. We'll just use output pin D5, which we haven't used before, just to be different. I think we will want a resistor between this pin and the speaker to limit the current that flows through the speaker. A speaker often has a low resistance, like 8 ohms. So I'm going to put a 100 ohm resistor here, so that if this is 3.3 volts, and it's going to toggle back and forth between 0 and 3.3 volts to play a tone. So this will be like a voltage versus time. So this will go back and forth between ground and 3.3 volts. And when it is in the 3.3 volt state, I don't want the current through the speaker to be too much. If this is 100 ohms and this is about 8 ohms, then this will be something like 30 milliamps. I think that's okay. Here's my 100 ohm resistor, and then this green wire is in pin D5. So here's 0, 1, 2, 3, 4, 5. So I will run this D5 wire over to this breadboard column. Then I will run this resistor over to here, and then I will run the green wire of the speaker. It really shouldn't matter which is which. The green wire of the speaker to ground. The speaker should be reversible, and the red wire of the speaker to the same little column that has the 100 ohm, the other end of the 100 ohm resistor. So there's my speaker. Here is pin D5. Here is where we connected pin D5. That's wired to the top end of the resistor. Then the bottom end of the resistor goes to the red wire to the speaker, and then the green wire from the speaker goes back to ground. And then this ground on the breadboard goes to this ground pin on the M4 board. Then we want to write some code. So starting from our previous code, we will say D5 will be an output. So there's D5, then we can erase this stuff. So D5 will be an output. We're going to say D5 dot value is true, and then we can say time dot sleep. Oh, let's think. So if we wanted 440 hertz, that is a period of roughly 2 milliseconds, 2.27 milliseconds. So in principle, we would want to sleep for 0.00136. Is this 1.36 milliseconds? I am going to guess that this will not be at all an accurate 1.36 milliseconds, but let's see. And then we'll say d5.value equals false. That's logic low. Time.sleep 0.00136. Let's see what that does. Okay, so we will say save. Oh, it's playing a tone. Now, one question is, did we get the period about right? But before we do that, let's make the period programmable. So we said that in fact, we can say period equals 1 over 440. So that should be about 2.27 milliseconds. And then we can wait period over 2 and wait period over 2 again. So this is half the period when it's in the high state. This is half the period when it's in the low state. And we should just hear what we heard a moment ago. So let's try that again. Okay, then now if I try 220 hertz instead of 440 hertz, if this were an Arduino, I think that would work. So I think we could just make all the times be twice as big, and we should double the period and thus cut the frequency in half. So I think you should hear an octave lower, but I think it's not going to work out quite that way on the CircuitPython board, because CircuitPython is a lot slower than the C code that runs on an Arduino. Well, it certainly is lower. Let's see how well we did. Let me try looking at the waveform with an oscilloscope, which graphs voltage versus time, to see how well we did at getting 220 hertz in this case. Somewhat to my amazement, I got my oscilloscope set up. I'm going to unplug the speaker again so that it's not quite so annoying. And we can see that there is a waveform of voltage versus time that this oscilloscope is graphing. I don't have a real oscilloscope in the recording studio, so I am using a Digilant Electronics Explorer board as my oscilloscope. It's actually an affordable way to get a kit of all kinds of measurements and a little breadboard at home if you're interested. There are actually some other boards by Digilant. There's one called the Analog Discovery board also. So this measurement claims that the period of our waveform is just over 4 milliseconds, 4.005 milliseconds. And if we go back to our Python code, our Python code was looking for a period of about 4.545 milliseconds. And it seems like we got more like 4.005 milliseconds. And if we change this to, let's say, 110, it should be, in principle, it should be an octave lower. Oh, so I'll play the old version and we'll compile the new version. It does sound lower. Let's see what the oscilloscope says. The oscilloscope says now a period of 8.01 milliseconds. So that is about an octave lower. It's about a factor of 2 longer period. Okay, so that's not too bad. An oscilloscope lets you adjust the time scale on the horizontal axis, and it lets you adjust the voltage scale on the vertical axis, and you get a graph of voltage versus time. And we were able to add a measurement which let it calculate the period. So I think the Python code may not be super accurate about its sleep time. On the Arduino, there's a function called microsleep that lets you sleep for a specified number of microseconds. I'm not yet sure whether CircuitPython has such a feature because CircuitPython is rather new to me. There is a really accurate measurement of time intervals that one of my students last spring used instead to try to get a precise tone. So basically it recorded the time at the beginning and then it looked at the time later, and based on the time difference modulo the desired note period, it made the output either be high or low. And that was a reliable way that that group of students found to make a tone sound good enough to play a musical scale. So if you're curious, that time function that my students last semester used to measure accurate time intervals, it's time.monotonic_ns, or I assume ns is for nanoseconds. But we're already out of time here, so I'll leave that for you to try. I hope you've enjoyed this very brief introduction to electronics and this application using CircuitPython to wiring up circuits using your newfound knowledge of Kirchhoff's rules. I think if you want to try some of these things out for yourself, the money that you need to invest up front to get a little board capable of CircuitPython and a little breadboard and some resistors and LEDs is not too big. Or if you don't want any external components, it looks as if the available boards from Adafruit are pretty modestly priced. I will tell you that learning a little bit of electronics is very empowering. It opens up a whole new world of tinkering for you. So if you have an opportunity to do that in the future, I strongly encourage you to give it a try.